hopefully she sends me an email. Okay, so I promised you last time a formula for calculating the number of your sample. How big does my sample have to be to get a particular margin of error? And here is the formula here. So let's suppose I want to get a 90% confidence interval. So that means the ZC that I'm going to use is 1.645. Let's suppose I want a margin of error of 1%. E is 0.01. Now, there is a little bit of jiggery pokery going on here. P hat can be a number. If it's not a number because you don't know, you'll use 0.5. But sometimes people will say to you, well, in the past, it's round about 0.7, let's say. So if they tell you to use that, you use it. If they say we don't know, you have to use a number. And 0.5 is the go-to guy, right? If you have no idea what the answer, what P hat is going to be like, 0.5 is safer. If through experience and you've done it lots of times before and you have some kind of value that you think is reasonable, then you would use that one. So here is our formula. So in my story, can we pretend that from past experience, that P hat is pretty close to 0.7, right? That's what it tends to come out as. Then the number of people in my sample will be 1.645 times P hat times 1 minus P hat, all divided by 0.01 squared. And so I'll go 1.645 times 0.7 times 0.3 divided by 0.01 squared, and I need about 3455 people. So I would need a pretty massive sample, right? 3,000's not cheap. If you want to do a survey with 3,455 people, you're going to spend some money if you want to do it properly. Okay, what do you think would happen to this number if I changed this margin of error and I was happy with plus or minus 0.4, right? So suppose I did a margin of error of 0.04. Do you think I need the same sample size, or do you think I'd need fewer people, or do you think I'd need more people if I'm willing to get a margin of error of 4%?
More people?
You think it's more? So 4% means your answer can be plus or minus 4. Let's find out then. Then it's going to be 1.645 times 0.7 times 0.3, because none of those numbers change. And the only thing that changes is that this guy is bigger. Now, if you have a bigger number on the bottom, what happens to a fraction when you have a bigger number on the bottom? Do you get a bigger answer or a smaller answer?
Using negative, right?
Yeah, well, let's see it. 0.7 times 0.3, all divided by 0.04 squared. And actually, maybe it's a surprise to you, keep it in red, you only need 216 people. So if you want a plus or minus 1% margin of error, which means you want your prediction to be quite a small interval, you'll need to do 3,400 and change. If you're willing to live with your margin of error being much wider, right, less accurate, you can get away with only 216 people. Now, a little idiosyncrasy, it's not a biggie, but I want to tell you right now. In my formulas, I use 1 minus P hat, right? You can see it here, for instance. It's also called in this textbook Q hat. So if you ever get a question and it says, what is Q hat equal to? Just take 1, subtract P hat from it, and that's your answer. So in this question here, wouldn't what they call Q hat be 0.3. Right, so just in case you see it, right? I think it's better to call it what it is. Isn't 1 minus P hat is what it is, right? That's how you calculate it. Otherwise, if you just call it Q hat, don't you have to remember that that means 1 minus P hat? So you're still going to say it in your head, even if you don't physically write it down. So that's why I prefer that. Are we comfortable with this? How to find, you know, how big a sample needs to be to get a particular confidence interval with a particular margin of error E, right?
Is this on the homework, the third one, chapter 7 at the end, where it tells you to find the margin of error?
Yes.
And you can, okay.
Well,
right,
it's in those questions, right? So
I was
it's
wondering,
in
I
that
was
section.
like, I don't know how to do this. I thought it was.
Okay. Well, hopefully this will help. I'm going to zip over now to the homework, and the section we're talking about is estimating a single proportion. So let's kick in here, save the guy, try and make it a bit bigger if I can. Boom, 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 boom. Here we go. And I don't want the solutions, they're a distraction. Out and in, here we go. Right, so can you remember we talked about, well, I've got a 5 rule, but that should be a 10 rule, so I'm not going to ignore that. For this problem, carry at least 4 decimal digits. I actually think we did this one, did we? Yes, we did. So that's the one. The one I'm trying, here we are. The one I'm trying to find is you can use the salt button, right? To find out intervals for that one, but I do remember the extrovert, so I'm trying to find one we haven't done yet. Oh, let's start with 4 then. In a random sample of 522 judges, it was found that 277 were introverts. You might say, you know, quiet people, shy people would be one way of describing an introvert. And let P represent the proportion of all judges who are introverts. Find a point estimate. That's just means find P hat. So if I do this, it would be 227 out of 522. But since the clue here is to 4 decimal places, I'm going to write that down in my calculator as 227 divided by 522. And the answer that I get to that is 0.4349. Now, I am not using salt right now. Let's show you how you do that question, including that answer, with salt. So you hit the salt button. Okay, good. I was worried about that disappearing. Right, are you all looking at salt?
Yes.
Yeah. Okay, so inferential statistics. Pick a 1 sample proportion. Do you see it's this guy now? Now, they've got a guy called the number of successes and a guy called the number of trials. The number of successes just means how many people said yes. 277 said, yes, I'm an introvert. Out of a total of 522. Do you see that's introverts out of total, right? Yeses out of total. Now, we go down here and we hit confidence interval. And I've forgotten what the interval was going to be here. I check it out. It's a 99, okay. So you want a 99, you make this guy 99. So 1 sample proportion, the number who said yes out of the total, click on confidence interval, and then you can generate the results. Okay. Now, do you see the P hat guy that we had? That's it. If you look carefully, can you now see the lower limit and the upper limit? You see those guys there? Right, so I'm going to move this out the way. Hopefully I can come back here, and all you do is you copy this guy and you plug it in here, and then you copy this guy and you copy it in here. So what WebAssign is doing isn't it doing all that p hat plus or minus, 1.96 times the square root of p hat 1 minus p hat over n. Remember that big ugly formula yesterday? Salt's just doing the whole thing for us. And to 2 decimal places now, that guy becomes 47 and this guy becomes 59. Okay. Now, it then says, give a brief description of the meaning of this confidence interval. So we are 99% confident that the true proportion of judges who are introverts fall inside that limit. Isn't that the one that a 99% confidence interval means, right? Somewhere between 47 and 59 is where the proportion of every judge is, right? What percentage of them? And I still don't like this, but you got to do what they do. It should be a 10, but this book does its own thing. Do you consider these conditions are satisfied? Would you agree that there's at least 5 people who said yes and 5 people who said no? So the answer is yes, it is. You can say that one or that one, whatever one they decide. I would think it's that one. Okay, here's the next one. A random sample of over 5,000 permanent dwellings on an entire reservation showed that 1,683 were of a style that they call traditional Hogans. So evidently Native Americans like a particular style of building to live in. That's fine. And we are looking at, I'll just write this number down, 1,683 out of a total of 5,160. So it looks like more people probably stay in modern style houses, for want of a better word, rather than the traditional style, which is okay. And do you see that funny P hat and now the Q hat I mentioned? See that there? Right, let's just do this guy in salt. I got the numbers I need, yeah. So one sample proportion, 1,683 out of a grand total of 5,160. And confidence interval of 99%. And all the numbers we want are here and here. So I'll move them out the way. Take this guy, and the proportion that are traditional are around about to 4 decimal places, that number, and the proportion for the upper limit to 4 decimal places. Oops, I put that in the wrong place. I apologize. P hat, right, the proportion is this number. That's the proportion. Into 4 decimal places, that guy's a 2. Q hat isn't in this, so I just take that away from 1. So Q hat is 1 minus P, so that's 1 or 0.6738, right? And then it asks us to find a 99% confidence interval. Now that's where I put those numbers that I put in the wrong place earlier. So the lower limit is going to go here. And the upper limit is going to go here. And they want this answer to be 3 decimal places, so they keep changing the accuracy. That's that guy and that guy. And these 2 answers are the standard ones. Now this guy is not obvious, and if you look at the WebAssign, it doesn't tell you. So I'm going to show you how to get the margin of error when all you know is the lower limit and the upper limit. So if you imagine this as a number line, and at this side you've got the lower limit, which is the smallest answer that you're likely to get, then you got your p hat in the middle, and then that's where p hat would be. I'm not even going to write it down because I'm not going to use it. And then you have an upper limit of 0.343. The margin of error is the distance from here to here. It's also the distance from here to here, right? So there's the margin of error. So from here to here, isn't that two margins of error, right? From start to finish, one either side. So if I wanted to find out what number this is, couldn't I just take the upper limit, subtract the lower limit, which is I'm now about to do? That's 4, that's 3, that's 0.034, which is 0.034. What did I do to that number to find the margin of error? I know from there to there is 2 margin of errors. I've just subtracted them, so I now know that that is 0.034. What do I do to get the margin of error?
Divide it by 2.
Yeah, divide it by 2. So it's a little bit messy, but I'm pretty sure you can do that. There's your answer. So if you ever want to get the margin of error, you simply just take the upper, take away the lower, and divide it by 2. Okay, so that's a different formula than the one we showed you. The one we showed you at the beginning of today is the formula to get the sample size, for a particular degree of accuracy. And question 6 is pretty much the same kind of story, so I'll skip by that. 7, we've done one very similar to that. Should I do 8? Yeah, let's do 8. So we're using, these questions are all using salt, so we don't need to do anywhere near as much number crunching by hand as we did in the other ones. So here's question 8. Case studies have shown that out of 10,324 convicts who escaped from certain prisons, only 8,000 were recaptured. I hope that's just made up data, because that would be scary if it was true, right? But evidently we're using those numbers. So 8,193 out of 10,324. And we are going to basically just do a pretty standard 99% confidence interval, because they seem to like that number. So when I hit use salt, here we go. One sample. Number of successes is 8193. Up to, or out of, I should say, 10,324. I want a 99% confidence interval, and we're good. So p hat is about a 79% of them get caught, right? Fair enough. And based on this sample, we have a lower limit of this guy and an upper limit of that guy. So I'm now going to put those numbers in and see what they might round off to. 4 decimal places, that 5 becomes a 6. The upper limit, and I just put that in the wrong place again, didn't I? Let me fix that in a second. 0.83, make that 8, and the upper limit, which is this guy, belongs there. Upper and lower, I should say. There you go. And p hat I got this guy here. Goes here. And to 4 decimal places. Oh, I put that guy in, right? Didn't I? Go figure. And the lower limit then is this fellow. Right. So after a few changes, I finally got everybody in the right place. Now, here's a question they haven't asked. If I tell you the lower limit and the upper limit, and that's all I tell you, we know how to get the margin of error. Don't you just add subtract these two guys and divide by 2, right? How would you get p hat? How would you get this number, or at least an approximate value, only using these two guys? So if you know the upper and you know the lower, how do you get the guy in the middle?
Subtract.
Oh, that's how you would get the margin of error. That's how we did the margin of error, right? We subtracted and halved it. Any suggestions?
You could average them.
Yeah, just add them in half. That would get you the middle, right? So if one of them was 5 and the other was 10, wouldn't the average be 15 divided by 2? Wouldn't the average be 7.5? And wouldn't 7.5 be right in the middle between 5 and 10, right? So it works perfectly fine. So if you needed that, the last two questions are pretty standard. You know, if they're going to do that, shouldn't they really just not bother after the first one? Because you're just going to answer the same time, same answer each time. What's this one about? Marketing, nothing interesting there. Pretty standard question. They changed the story, but not really what you do. Try to find something that's got a little bit. That's it. That's all I got for you. So if I gave you a question that had the salt button, do you feel comfortable you would be able to get the confidence interval using the numbers in the story? They basically, that's the go-to question in almost all of these cases. So what we're going to do now is the last part for this week. And we are going to look at, I've got my little list, here we go. How do you estimate the difference between two proportions? So let me return back to my white screen. How do you estimate the difference between two proportions? So I'm going to show you, one, how to do it by calculator. And two, how to do it using salt. And we're not going to do very many by calculator. It's quite long to do. And since there is software that is, Salt is going to do it for us, it kind of makes sense that in practice, wouldn't you use a salt button or the equivalent software if you wanted to do things, right? You wouldn't really necessarily do it by hand. But I want to show you how you do it by calculator, by hand. So we're going to have two populations because we are interested in the difference between the two populations, proportions. Right. And since it's my question and I'm making up the data, we are going to have women and self-identified men, right? And we are going to ask them a question. And the question we're going to ask is very sexist, and that is, do you enjoy shopping? Right. Now, if you're anything like my wife, she will deny this, but I will say she does. My wife has got a couple, 3 sisters, and when they come over and they visit, do you know one of the social events that they do is they go recreational shopping, I call it. They go to stores and they try on dresses and shoes and they look at them and say how nice it looks for them. and all that stuff. And the only way you would ever get me to join them would be by gunpoint. So I do not like recreational shopping. So I'm not talking about going for tins of beans, right? I'm talking about going shopping because it's fun, right? To buy things and try them on and do so on, right? So that's my sexist story. So they found a random sample of 100 women, and 57 out of that 100 said, yes, I like doing recreational shopping, right? I like shopping for fun, right? Trying on clothes and whatever. And then they got 200 men, and and they asked them, do you like to do this recreational shopping thing? And there's 94 of them that said, yeah, me recreational shopping is going to Best Buy and looking at all the electronic stuff and trying the headphones, right? That's recreational shopping. You're not really probably there to buy stuff, aren't you? You're just there to see what cool stuff is there and can have a wish list for Christmas. So guys do it as well, right? So the question is there a distinct difference between the two groups, right? Are they essentially the same, or are they any evidence to prove that one is bigger than the other? Now, when you look at fractions, it's a little bit difficult to tell which one is bigger right away. So I'm going to do converting this guy. I don't know why I used my calculator. That was obvious. 57. And this one is 47. Would you agree that at least superficially that more women, percentage of women, like recreational shopping than guys, right? But we know that that could just be a fluke of data. Couldn't you get a sample where there was a lot more women than there typically is, and then a lot less men than there typically is? So we can't base it just on that, right? The point estimates. We have to create a confidence interval. And so I'm going to create a 90% confidence interval. And I'm going to show you the formula for it. P1 hat take away P2 hat. So we're going to find a 90% confidence interval for the difference between the two. So P1 hat take away P2 hat. Oh, that's pretty obvious. Would you agree that's the difference between the two, right? Plus or minus 1.645 times the standard error. And that now becomes P1 hat take away P2 hat plus or minus 1.645. And this guy called the standard error has a really ugly formula. It's P1 hat, 1 take away P1 hat all over N1 plus P2 hat, 1 take away P2 hat over N2. Where do you think this magic number 1.645 came from? Do you recognize it? 1.645?
Is that the 90% CI?
Yeah. If you wanted a 99, wouldn't you make this 2.58 and leave everything the same? And if you wanted a 95, wouldn't you make this number here 1.96? Do you see how these magic numbers, as I'm calling them, they transfer to lots of different situations? Now, this is horrendously ugly. But if I cover that guy up, isn't that the formula for the standard error when it's one sample? And isn't that the formula for the standard error when it's one? So can you see that the formula sort of makes sense that you're just adding two standard errors together inside the square root? So since this is going to be the only one that we are going to be doing, numerically, right, using the calculator, let's continue onwards. Then it's going to be P1 hat, which is 0.57. Take away P2 hat, which is 0.47, plus or minus 1.645 times the square root of, yikes, here we go. The first guy, 1, take away the first guy, all over 100. So that's P1 hat, P2 hat, 1 minus P1 hat over M1. Added this guy, 47. Take that away from 1, 53, all over 200. Now that guy, take away that guy is 0.1. Plus or minus. Now this entire horrible mess from here to here, right? That's big, massive calculation, right? That guy there. That's your margin of error. You remember the plus minus guy? That's your margin of error. The good news is that although it is really ugly, you can do it in one go. So 1.645 times the square root. And I'm just going to type this guy plus this guy. So 0.57 times 0.43 divided by 100 plus 0.47 times 0.53 divided by 200. And wow, that's just a fluke. Isn't that a really nice number? Right? To 2 decimal places then, isn't that 0.10?
I have a quick question.
Yes.
On this underneath over the 200, where'd you get the 47 and the 53 from?
Oh, 47 is P2 hat. And take that away from 1 and you get the 0.53.
Oh, okay, I see.
Now,
Thank you.
that was a sheer fluke. And in a funny sort of a way, I don't want it to be that number, but it is what it is. That's 0 to 0.2. Can we pretend that that number is 0.00001? Just pretend it's a little bit bigger than 0. Because what we can now say is that since all these numbers are positive, doesn't that mean that the difference between the two is positive? Can we pretend that's positive, 0, right? And if that's the case, doesn't that mean that I have just managed to prove that women like recreational shopping more than men on average? So if your interval has nothing but positive numbers, you can make the conclusion that the first population's proportion is bigger than the second. If your interval was nothing but negative numbers, which this interval is, won't your conclusion be that the difference between them then, because that's what this interval is representing, has to be negative, right? And doesn't that mean you've now proved that the first population is less than the second? And what do you do if your interval has essentially positive and negative numbers in it, right? It contains 0. What conclusion, if any, do you make about the difference between these two? Can you make any conclusion?
It's inconclusive.
Yeah, inconclusive. You're right. Basically, that just means we can't tell. We don't know. So can you just pretend that said 0.01? Because it's a fluky numbers that it ended up being exactly 0. Which proves you should never randomly pick digits unless you know what the answer is going to be. But that's cool. So that's how you do it by hand. Would you agree it's a bit ugly, a bit messy, but eventually you'll get an answer, right? So you can do it by salt. So let me show you a situation where you might want to do that. Let's pick a medical story. Population 1, and we're going to do this using salt, but this is the story being set up. Population 1, and then we're going to have another population 2. And we're going to set up what's called a clinical trial. Right. In the medical world, right? Clinical trial is normally a term that you use that you've set some experiment up to see if one form of treatment is better or worse than another, right? In my story, there's going to be let's say it's a cancer treatment. And population 1 get the old treatment, right? And let's say the old treatment is a combination of chemotherapy and, pills. And if you do the other one, we'll call them the new treatment, right? The brand new drug. Right? So they're getting this new drug and they're getting the old drug. So both groups get the same chemotherapy. The only difference is that one gets one pill and the other gets the other. And there are some pills that are very good at treating cancer. I mean, one of the ways that they work in lots of different ways, but one of the ways they work is that they get absorbed by the cancerous cells more than they get absorbed by the healthy cells, and that the chemo is designed to target cells that contain this chemical, right? So you kind of make it, you kind of put a bullseye on the cancer. So when you're doing the chemotherapy, it makes it more effective, right? That's one way. There are many other ways that they do it. And we would like to know, is this new drug better than the old drug? So you normally have a thing called success. So a success in a cancer treatment might simply just be, what percentage of your patients are still alive 10 years later, right? Because people die of all sorts of other things, right? So you can't say they're going to live forever, right? Because that would be a stupid way of measuring anything, right? So how many are alive in 10 years from now? And in the old cancer treatment, there was a sample of 200 in that trial. And 10 years later, you got 180, right, out of 200. So that would be a really good drug. Would you agree? A 90% success rate is really good. I wish all cancers were like that. Some cancers are really good at being successful, right? There are just some cancers that they're really good if they catch them early, are really successful. So you would think that would be a pretty hard drug to beat, right? It's got a 90% success rate. But, technology changes and pharmaceutical industry. They had a new drug and they had 100 people, and in their drug, 94 people were alive. Right? So there we go. Would you agree, again, superficially, isn't drug 2 more effective than drug 1, right? Its success rate is 94% against 90. And if that was true, if we could actually prove that this new drug was more effective than the old drug, wouldn't there be a good argument that we should all start using the new drug? Because even an extra 4% success rate, isn't that 4 more people living that wouldn't be alive today because of it, right? So it's worth it. Even a 1% improvement is still worth it. I mean, in the medical world, aren't treatments incremental, right? You just get an extra couple of percent each time you do something. You increase the chances. That's what we're after. Of course, it may not be that this is evidence. Couldn't it just be the randomness of the things? So, background to this. If you're going to do a real clinical trial, you get 300 volunteers who've got the cancer that you're treating, right? Yeah. And there are ways that they can do it. Have you ever been listened to the radio and they say, we're looking for a clinical trial on a new drug for arthritis, right, or whatever it is, right? And you can apply, and then you've got a random sample, in this case, a total, that's a 100 here, by the way, 300 people. You randomly put them into 200 in this group, in this case, and 100 in that. Now, you might say, why not 150 and 150? That would be the best way to do it, wouldn't it? Equal size groups. But sometimes they can't do that. When you've got a new drug, isn't one of the things is you don't actually make a lot of that drug? You know, it's almost like you do each pill individually. And so you can't generate enough treatments for a large number of people, right? So sometimes you have to do a smaller group. That's not uncommon. And the reason it should be random is, in any case, aren't there some people who are in the early stages of this cancer, and some people are in the late, the latter stages of that cancer? And some are pretty healthy, right? Early stages, some are really seriously ill. And isn't it only fair that each group has a bit of both? Right, so it's a fair representation. So the only difference between these is the pill that they took. And now we'll move on to using salt. I've got all the data that I want. There's one last thing I want. I have to choose which confidence interval I want to pick. I can have a 90, I can have a 95, and I can have a 99. And I know which one I want to pick. And the clue I'm giving is, isn't it very serious if you get this wrong? In other words, if you say, oh yeah, use the new drug, it's better, and actually it wasn't, aren't you hurting people rather than helping, right? So based on that very big clue, what kind of confidence interval do I want?
99.
I want 99. So if I'm doing anything in the medical world, right, anything that's going to involve people's lives, I want a 99. I want to be saying, look, I know I can't ever be 100%, right? I'm never going to get that. But at least 99 is as close as practical, right? So everything is here. I'm now going to nip over to salt, and we'll show you how you put all that information into salt. So I'll click on salt. I'll put this over here. Bear with me for a minute. There we go. Okay. Now, inferential statistics, that's kind of where everything has been lately. Here is the list. I think it's self-evident. Which one of those should I be choosing for the difference between two proportions?
Two sample proportion.
Right, agreed? Now, sample one is going to be my population one data, and that was what, 180 people out of 200. And the second one is going to be those who got the new treatment. So that's going to be 94 out of 100. And then I'm going to do a confidence interval. And we decided that since this is really very important, that I'll do a 99. And all I need to do now is hit generate results. Now, if you look at this, do you see it's negative 0.12 up to positive 0.04. So let me go back to the white screen and see how we would interpret what we've just found. Doesn't this interval have negative numbers and positive numbers? Agreed? Negative and positive. Whenever you have an interval like that, it is inconclusive. Any one of these numbers from here to here could be the right answer. For instance, if the answer had been that the difference between them was positive 0.02, right? That the difference was a positive number, doesn't that mean that we've actually got evidence that that's better than that? Right? So you are looking for situations that look like this. If all of them are negative, doesn't that mean that the difference is negative And so P1 is less than P2. Isn't that what we were hoping for in this story? Right, the success rate for the old drug was less than the success rate for the new drug. If, God forbid, it happened, but if you got this as your answer, wouldn't that mean in the context of this story that the difference was positive? And wouldn't that be, don't use the new drug. We've actually proved that the old drug is definitely better than the new drug. Now, what we've got here is pharmaceuticals nightmare, the company. If they get this one, they are saying, hey, we've got a new drug treatment out here. We'll, send our data, the FDA will check it all, bang, we'll start making it. And, they charge $2,000 a treatment because isn't that what they charge when a new drug comes out? Some ridiculous amount, but, that's what they do. And that, people will live longer, right? And if this comes out, won't the pharmaceutical company say, well, that drug was no use, throw it in the bin, try something else. But what do you do if you're a pharmaceutical company where it's inconclusive? The reason why that's a nightmare to them is that it's very expensive, isn't it, to develop a drug, to check that it actually is successful, and then get it through the FDA, because they have to check for things like, safety and long-term side effects and, all the other things. That's a very expensive process, which is why they charge so much money when they get a success, because don't they have to, for every successful drug that a pharmaceutical company comes out with, there's probably 9, that ended up failing, right? But they spent all that money and got nothing out of it. So I'm being a bit unfair when I say they charge an extortionate amount, but they probably do charge more than they should. So if you're this pharmaceutical company, let's go back to it. Do you think it's worth trying again? Could you just have been unlucky with your data? So you've got 2 options. One is, well, 3. One is, nah, I'm not spending any more money. This isn't working. Option 2 is, I'll just do it again. I'll do another clinical trial and see if I get, for want of a better word, good data. That's not really a good idea, isn't that? Just rolling the dice until you get the answer you want. Right. Oh, I'll just keep doing it and keep doing it, because one of them's going to probably work eventually if you do it often enough. The third possibility would be if you believe that your drug is, in fact, a better choice, right? Couldn't you just do bigger samples? Do a really big 2,000 here and 1,000 here, right? Spend a lot of money. Because if you spend a lot of money and do big samples, you will be able to narrow this interval down, right? Because the bigger the sample, the smaller the interval becomes. And if it becomes small enough, couldn't you get to the point where you would really have evidence that everybody is negative? Right? Can you imagine if this one shrank in both directions equally? There's no guarantee it would. But if it shrank in 0.05, this would end up being 0.7, and this would end up being 0.1. Would you see in that case, there is evidence now, isn't it effective? Now, there's no guarantee it's going to, shrink in equally. Couldn't it shrink in a lot more on the left and nothing on the right? In which case you could probably just say, okay, time to leave. This isn't working, and call it good. Liana, have you ever had any experience of clinical trials being done? Not you personally, but people around you, or things happening in your hospital?
I work in the ER, so not so much in the ER, but at like a lot of teaching hospitals, they'll do like different kinds of trials. I've had a friend who worked at a different hospital and was like part of trials. Like didn't know, I think they were double blind, so they didn't actually know like what was happening, but they knew a trial was happening. And then from data, they figured things out of like who had it, who didn't. But
it's interesting to see actually how they do the process behind it.
Yeah.
This is not just a baby version of what they do. This is what they do, right? This is how the process works. So you can look at that data now, and hopefully if you ever you know, if you're reading papers about a new treatment, you'll be able to say, oh, okay, they did this and this is the confidence interval, and I now
Yeah.
know why they said it worked or why it didn't work. I'm doing a 99 because I think cancer treatment is very important. But if it was just a, well, I don't know, a headache pill, you know, the kind of pill you take if you get a headache, right? I think I could probably live on 90%. Would you agree that the worst case scenario is you still end up with a headache, right? So, you know, this number doesn't need to be fixed in stone. It can depend on what the particular, for instance, what if you want to share, what was your friend's treatment? Can you remember what she was being tested for or not?
I don't. Like, she worked at the hospital, but she wasn't in the treatment.
Oh, she
but
was.
I
right.
did have a friend who was in a treatment for her baby. She was pregnant and their baby had like growth development issues. So
Right.
she was in this trial in like Ohio. Basically, like, she didn't have enough amniotic fluid, so they were like giving her fluid to see how long like all the babies would last if they would make it to birth, essentially. And she was the longest one who lasted in the trial.
I hope it ended well for her.
It didn't. I mean, like, her baby lived for a couple hours, but that's about it.
Yeah.
It was sad. But I mean,
sad. Yeah.
she was the longest one in the trial. So like, clearly they're doing things that are helping, but it was rough.
And I sometimes you have to have failures to learn so that you do better the next time.
Exactly.
Yeah. But yeah. No, I need to, that was sad. Right.
Yeah, it was super sad. But I mean, like, she was more or less happy that she did it, because she's like, you know, I didn't really have anything to lose at this point. And her
Right.
baby.
You do what you do for your baby, and you know,
Exactly.
if it didn't work, at least you did it.
Exactly.
Makes perfect sense to me. Right. So this is basically how you compare then two populations, right? Population 1, population 2, and you just take the information that they will give you in the story, and you'll have something out of this total, something out of that total, and you'll create a confidence interval. And then you'll say, is there enough evidence to prove the first guy is bigger than the second proportion? Is there enough evidence that the first one is less than the second? Or is it inconclusive, right? That's pretty much what all these stories are going to look like. So I'm now going to nip over and show you what the homework version of each of these questions look like. I wish they'd pick better, more interesting stories, but you know, whatever. So let's do this one. On the Navajo Reservation, a random sample of 228 permanent dwellings in Fort Defiance region showed that 64 were traditional houses. Okay, so population 1 is going to be the traditional ones, and I'm going to call that 64 out of 228 houses. Okay. If you went to Indian Wells region, there's 23 in that place were traditional, and so that's 23 out of 139. So all the numbers that we need to do this are here, right? So these two numbers gave me P1 hat, and these two numbers gave me P2 hat, right? And I wish they'd put a 90 or a 95 sometimes, right? Just to be different. I mean, it's not a biggie, but 99 it is. So I'll hit use sort. We'll go and do the two sample proportion. And the first one was 64 out of 228. And the second one was 23 houses were the traditional style out of 139. And so what we're going to compare is two different native reservations and the percentage who had traditional houses, right? Traditional native style houses. And confidence interval on 99% and generate the results. So here is the difference. The first lot is what, about 11.5% bigger than the second. Here's the lower limit and here is the upper limit. So I'm going to go here and hopefully, are you now looking at the original question 1? right? So I'll try and make sure I put them in the right place this time. The lower limit as a decimal is that guy, into 3 decimal places, that rounds off to a 4. And the upper limit, which is this one, to 3 decimal places, that ends up as a 7. Now I'm looking at this, would you agree that's all positive numbers? The difference is positive 0.004 up to positive 0.227. Doesn't that mean then that the first group has a bigger percentage of traditional houses than the other place, right? Population 1 is bigger than population 2, right? Everybody is positive. 1 is bigger than 2. And that's the sentence that you're going to get from. Because the interval contains only positive numbers, we can say a higher proportion in the first place than the second. Done. Now, that was about traditional houses, and nothing against that kind of evidence. But isn't that the same thing you could use with old treatment, new treatment, if you were doing medical, right? Or how much money we made when we did the old way of advertising and how much money we now make now that we're doing the new method of advertising. Because you can see you could use that in business, couldn't you? Right. We did a lot of radio and not much TV. How much sales did we get? We changed it. We did a lot more TV and less radio. How much, sales did we get? And then if you're in a business, won't you obviously pick the strategy that's most successful? So this comparing two things really makes sense. Top of my head, can you imagine they've got 2 alloys, right? The old alloy, how strong it was, and then they've got this new alloy, how strong it was. Wouldn't you be able to test the strength and see, is the new alloy actually better than the old alloy, right? You could compare them in the same way. Okay, that's boring. Don't like that story. Okay, number 3, like this one. At Community Hospital, the Burn Centre is experimenting with a new plasma compress treatment. Is that a real thing? Does anybody know? A plasma compress treatment. I have no idea what that is.
I don't know about compress, but I definitely know like that's a thing.
Okay, so they've got this new thing, right, called plasma compress treatment. They'll probably end up calling it a PCT, won't you? Because that's what they do. Everything in medicine, they make it letters, right? So they get a PCT, and this is a new way of treating burns, evidently. So they have a random sample of 330 patients with minor burns, and they get the PCT treatment. Of these patients, it was found that 262 out of 330 had no visible scars. So this treatment isn't to just fix the burn. It's to try and fix the burn and not leave a scar, right? Because, I mean, you could just fix it. Couldn't you just put a bandage on it and it would heal, right? But you probably get a scar if you tried that, right? So I'm just writing these numbers down because I need them. So for the first population, this new treatment, 330, 262 didn't have a scar, so that's what we've got. Another random sample with minor didn't get this treatment, so they would be the control group. And there were 418 of these patients, and oh, that's not good. 99 of them didn't have scars. So if you come in with a minor burn, right, they put the antiseptic on it, they clean it, they do what they do, right, and they just put a gauze bandage on it and say, you're good to go. And then the person's fine, but they have a scar. And then this new treatment looks to me like it's pretty good. Looks to me like it's a lot better than the other one. Find a 99% confidence interval, right? So I'll hit this guy. I'll bring it on. 2 sample proportion, and you're going to get a really interesting result. I'm pretty sure 262 out of 330, and only 99 had no visible scars out of 418. And did they mention? Yep, 99 because it's medical, I guess. And here is our answers. Lower limit, upper limit. The lower limit for the difference was that. The upper limit was that. And I'm going to round it off to 3 decimal places. So that's 479. And that's going to be 636. Now, that number is the difference between them. Doesn't that mean the new treatment is at least 47% better and could be as good as 63, 64% better? In other words, if that was a true story, shouldn't you be using this plasma thing? Right, the CPC. Now, not all treatments that are successful make it to general usage. Some of the problems. It might be good at fixing what it's fixing, but couldn't it have side effects? And if they discover dangerous side effects, like, okay, you won't have a scar, but your kidneys might fail on you. That would not be a good swap. Would you agree? Certain things can have bad side effects. If there's enough people with bad side effects, a lot of drugs just don't make it because of that, right? So that would be one example of why it might not be effective. It doesn't mean, however, that if someone got a treatment and they died, that the thing would get banned. And you might think, oh God, come on, if someone dies of a treatment. The reason for that is every single drug in the universe that you get in medicine, Lana, I hope you can back me up on this, isn't there some poor soul in the world who could probably be allergic to it and die?
Yeah.
Right. Now, does that mean you stop giving people aspirin because there's 1 in a million people who will die? No, right?
No.
You still do aspirins, right? And do you stop scar treatments because people die? It is basically a risk analysis, isn't it? Which is, what is the benefit? What are the dangers? What percentage of people fall into that danger? True story, when I was teaching back in Scotland, we had a student who was highly allergic to peanuts. I mean, drop dead, possibly, if he was allergic to it. So we had to, because I was teaching this particular student, this student had, I think it's called an EpiPen. Are they still called EpiPens?
Yeah, they're still called EpiPens.
Right, and it had whatever you give him if he got peanuts. And so
epinephrine.
Right. And so basically, they trained us how to use it, because the chances are if he, went into, is it epileptic shock or whatever the fancy name is?
Anaphylactic.
That one. If he went into shock, he would be in no state to do it himself. So
Correct.
we were told, he keeps it in this pocket, get it out and just stick it in his bum. So that was what we were told to do. Thankfully, it never happened. But would we ban nuts because he would die? No, we don't ban nuts, right? So I can't say it's funny because it isn't funny, but have you ever noticed, and me and my wife kind of laugh at this, that you'll see a TV program. America is really good at advertising medications, a lot more than you do in Britain. And you'll get one for, make it up, hemorrhoids. Right, and they say this hemorrhoid, blah blah, it'll do good, blah blah, and that's good. And your first thing I'm thinking is you'd never see a hemorrhoid advert in Britain, but that's not the problem. When they're finished, don't they always give you a list of side effects? And I'm exaggerating, and it's some side effects include liver failure, brain aneurysms, and heart attacks. And then after that, I'm thinking, hemorrhoids don't sound like such a bad problem anymore. And I think they only do that for lawyers' reasons, don't they? Because only maybe one person in a million did that happen to, right?
Yeah, it's always that like one lone person that if they don't say it and they're like, well, I was never told this, even though a lot of it's like listed on the bottle and like
Yeah.
list on the stuff. Like if they don't actually say it, someone will be like, well, no, they said it wasn't a thing and now it's a thing, and here I am.
So that's it. So all that happens is somebody, had a brain aneurysm, and
Yeah.
they might not even be that the hemorrhoids done it, but they had the hemorrhoids and the brain
Yeah.
aneurysm.
So
So
yours
let's play
sounds
safe.
like a lot of it will happen like when they do the clinical trials. Like that's what they'll test for like a bunch of other stuff. Like, hey, we're only looking at this specific thing, but like you may be that one person that something actually happens to. They're like, oh, okay, this could be a thing. This could be a thing, depending on like what other medical issues you've had, that it would possibly be some sort of situation. So like a lot of the things are like, oh, maybe, cause for blood clots. Like a lot of things can cause blood clots. So like they have to put it in there, even though it may not. Like your body may react to whatever chemicals in this that can cause you to have a blood clot. And if they don't say it, then they get sued.
Makes sense. Yeah. So when they're doing the clinical trials, any side effects like nausea or whatever that occur during the trials are included in the warnings if it ever gets to production.
Yeah. So if you get like nausea, like vomiting, anything like that, that's an actual reaction to it, and it's bad. So like the EpiPen thing you're talking about, like if he were to be around peanuts, anaphylaxis is pretty quick, which means like his throat just closes up and he stops breathing.
Mm-hmm.
That's like worst case scenario, and usually one EpiPen isn't going to do enough.
Oh,
So
well, I'm glad I never. I'm glad
so a lot
I
of
never
times, like
had to do that.
depending on how severe it is, like usually they can get like one EpiPen and like have to go to the hospital like immediately because they'll have
Well,
to get
maybe
a lot
that's
more.
it. You bang them, and then obviously you wouldn't
It's enough
just
to
say
like hold them over
to get them to hospital.
sometimes. Yeah.
Yeah, sometimes. Yeah. And I got to get this out because my brain does things and then I wander. So I got to get this out. In Britain, I was allowed to do that. I am not a medical person.
Yeah.
But I was
Anybody
told
can do EpiPen.
if he had it, this
Yeah.
is where the pen is, bang it in his bum. That's all I needed. I didn't even need to unclothe him. You just push it right through the clothes.
Yeah. So they usually tell you, depending on how little they are, like for adults, it's in your upper thigh. So they're like, just slam it in their upper thigh. It doesn't matter if they have clothes on or not. You don't need to be a medical professional. Like EpiPens are the most easiest thing, and I think that's why that they just give it to whoever, because like it's so simple you can't mess it up.
Right.
And it's
Why
really,
is it-
really using it in a life-threatening situation. It's never like, hey, I just need to like give this to myself for a second. Like I'm gonna die if I don't get this right now.
Yeah.
And that's
Gotcha.
why.
Interesting.
We had kids stop breathing after like waiting after getting their COVID shot.
Say that one more time.
We had a kid stop breathing at Walgreens after getting their first COVID shot, and our pharmacist had to give like a epi
A
shot.
bunch of epi, yeah.
Yeah, and then we just waited until the medical, the EMT got there and they took them. But that was kind of scary.
Yeah,
Oh,
it's
God.
and like when it happens, it's super, super scary, and like especially with kids, like it can go sideways very, very quick.
Wow.
Yeah.
We
That's why, like, with
need to
kids, they're
we
like-
need to move on here, guys. Sorry,
Yeah.
but it's very interesting, but it's also very depressing. So
Yeah.
let's look just at another example. I'm looking at my time here. So what have I got to do? Right, let's do two more questions. One is a little bit bigger than the other. So what we're going to do is question 4, where we're looking at this one, where we're actually going to find the upper and lower limit for each population separately. And then we're going to do it for the difference, right? So, and then the last one is just going to be a normal standard one, right? They're all SALT questions. So here goes. This is question 4 I'm looking at. In the focus problem at the beginning of this chapter, which I'll assume that if you read the book, you would know about it, the study was described and compared the hatch ratios of wood ducks nesting boxes. So population 1 were given boxes that were separated from each other and are well hidden, right? So you're trying to get the ducks to lay lots of eggs, I guess. Now, if you did it using boxes hidden, all that good stuff, there was a total of 450 eggs in box 1 and 272 hatched. So there's the number that I really need. 272 successes out of 485 of those boxes. And then the second way of doing it, group 2, they were put in very visible locations and they were all put together like in little bunches. And maybe that is a better way to do it, or a worse way. There were 274 out of 799. And we are going to look at the first one hid, the second type out in the open. And we're going to see what that looks like. Now, the first thing they want us to do is just do a confidence interval. What number do they want? A 95, good. So we're going to do a 95 on a 1 sample, right? So the first one is the hidden ones. So 272 out of 485 and a confidence interval like 95. And that generates 0.51 to 0.60, right? I'm just writing that down, right? So roughly 51 to 60% success rate, right? If the ducks have their nest hidden, that's how many actually hatch into little baby ducks. Now, if we then go back and now do it for the second group on its own, there were 274 successes out of 799. And when I generated that one, we only got about 31 to 0.37538 to 38. Would you agree that the second way of out in the open wasn't as successful, right? So we can now put the package together. So a 2 sample proportion now. We put in the data just like we did before, 272 successes out of 485. And then the ones out in the open, well, there was 274 of those out of 799. And we'll do a 95% confidence interval. And the difference that we got this time is 0.16 to 0.27, right? So that's me got all the numbers. So if you were doing the first interval on its own, it was a 51 to 60% success rate. And I'm doing it to 2 because I did it to 2. If you did the second group, they had a success rate that was somewhere between 31% and 38%. So when I was saying the first is more successful than the second, you just see that's pretty clear. Now, if you do a combination, right, the difference between the two groups, the lower limit ended up being 16 and the upper limit ends up being 27. And all of these are positives numbers, right? Every single one of these differences represents a positive number. So that must mean that this is positive, which in turn means that the first group was more successful than the second. So you pick the sentence that basically does that. And who should we do for the last one then? That's ducks again. I don't want ducks. Okay, for our last question, most married couples have 2 or 3 personality differences in common, right? So it could be your sense of humor, or it could be, do you like traveling, or whatever it might be. So a random sample of 378 married couples found that 128 had 3 preferences in color, right? So the first group are those who had 3 preferences. And so that would be what, 128 out of 378. Another sample, 580, showed 222. So the second group was 224 out of 580. Okay, and we are going to find, is there any difference in this. In other words, is one percentage bigger or less than the other? So the first one is this group, and the second one's that group. So got salt already set up here. Here we go. Two sample proportion, and the first group, there's 128 out of 378. And the second one was 224 out of 580. And we're just going to calculate a confidence interval. Let's say it's 95. I guess I should check. It was 99. Okay. Well, let's say it's 99. Now I'm about to hit generate results. If the interval has nothing but positive numbers in it, doesn't that mean that the percentage of married couples that share 3 common traits is bigger than those who only share 2, for instance? Let's find out what the result was. And it was a negative up to a positive. Do you see those two guys? Negative, roughly negative 5%. So I'll copy this guy and put it here. And the upper limit for the difference between the two is about this number. Into 3 decimal places, you get 5052. And to 3 decimal places, you get 115. Now, since this interval is both negative and positive numbers, isn't that inconclusive? We really don't know if more people have 2 things in common compared to 3 or vice versa, right? Can't really tell. And so you should pick which. So in this case, it would be that one. Are we good? Do we have any questions before we kind of do the tidying up for today? And any questions? Okay, last name and bye-bye. I'll hang about at the end if there's any questions that you might want to do, talk to me in private about.
Hey,
Hey Zach, you got
hey,
a
let's
question?
go. Yeah, I did.
Right, what you got?
I got it pulled up right here. I got really stuck on it yesterday. It's on. I'll just share my screen with you. Probably be easier.
Okay, I can do that. Here you go. You've got permission. Share the screen.
Okay. Oh. All right. So
Gotcha.
I'm having problem with how to do this right here to get that.
Right. So this is find the sample size question. Great.
Yeah. Yeah.
Right. So the formula that we're going to use, I'm writing this down and you'll see it in a minute. But what is the formula? Okay. So it's going to be a 95% confidence interval. Do you see that guy there? 95?
Yeah. Yeah.
So
Yeah.
I'm writing that down. And the margin of error, which they call E, is going to be 1.14, right? No, that's interesting. Can you scroll up a bit, because this one here seems to have a whole number.
You see all that?
Yeah. Okay, so you are doing the margin of error formula for a mean, not the margin of error formula for a mean, right? Oh God, I said that back to front, right? Okay, I know what I'm doing. Okay, so you have got here a sigma of 1.87, and that's important. And we've got a 95% confidence interval. and we have a margin of error of 1.14, right? Okay, I'm going to take control again and show you how you would calculate that.
Correct.
So, host only, there we go. So, the number that you need, the formula for calculating the number, is altered a little bit. Since it's a 95% confidence interval, the number we're going to use is 1.96. So it's going to be 1.96 squared, right, divided by this fella, squared, and then times. Now, it was originally the one we showed you today was that guy. Remember him?
Was that for a sample
Yeah, that was for a proportion one, right?
proportion? Okay, yeah.
Right, so the guy that would go there would be this, right? Now, it's not the same thing, right, when you have a mean, because the mean, the standard error isn't this guy, right? So I'm going to have to create the new version of this formula. So I'm going to call it ZC squared. That guy is going to be E squared. And now I just need to figure out is what goes here. And I'm going to do it from scratch. You don't need this, but I'm just doing it so I can figure out what the formula is. So we know that it's X bar, right? Plus or minus the magic number, which is what, 1.96, times the standard error. And the standard error is that guy, right? And this bit of the formula is the margin of error, which they're going to call E. So I'm starting off here. And I'm after N, so doing a little cross multiply. And then I'm going to divide by E. And then finally, I'm going to square everybody. Oh, and now I have the formula. You put sigma there. So you put in 1.87 in this case, squared. So the magic number squared times the standard deviation of the population squared divided by the margin of error squared, right? So the general version of that formula would look like this. Right. So what do I know? I have 1.96 squared times 1.87 squared divided by margin of error 1.14 squared. And the answer I get is about what, 10.3?
Yep.
So I'm assuming that that 10.3 will get rounded off because you can only ask 10 people or 11 people, right? So I'm going to give you permission again to share your screen. Okay.
Says
Can
I
you
can't
share
share it. Says
You
no.
can't share it?
No. Cannot share screen while other participants. Okay, there we go. Probably let me do it.
Right,
now.
let me.
There we go. We good.
Right, you got it? Okay.
Got it.
So we're going to type in 11 here. And if that doesn't work, we'll type in 10, but I'm hoping it's 11. So in D, type in 11.
Okay. So type it in 10.
11 first, I think.
Oh, 11.
Yeah, I would probably round up just to be safe. So that's what I'm checking right now.
There we go.
There we go. Okay. So it's just a formula that you're going to have to write down. And so that we're all really clear on what that formula is, I'll do it on a brand new piece of paper, right? And I'll write it down with I'll keep it nice and general so you can use it for any situation. So
Perfect.
the number you sample should be the magic z-score, right? The 1.96, whatever it needs to be, sigma over E, and all of these three guys are squared. So ZC, for instance, will be 1.645, or it will be 1.96, or it will be 2.85, and you use this guy if it's going to be a 90% confidence interval. This one you would use if it was a 95, and this is what you would use if it was a 99. E is whatever the margin of error should be, and sigma is the standard deviation that they will tell you. So you will be told that's 1.9, that this is 2.7, and that it's a 95%. Because once you know these three guys, there, and there, you're good. Now, the only thing you've got to be careful of, and it happened in that question here, is that if you get an answer like 13.1, or you get an answer like 13.7, both of them are 14.
Oh, so anytime it's above the number, you just round up.
Yeah, and the reason for that is to be absolutely sure, shouldn't you have one person more? Because if you did it as 13, which is the rounded off value, you might be just a little bit out. So to be safe, always round up in this type of situation.
Right. I think I missed it when you were putting that one up there. So thanks.
Are we good?
Yeah, absolutely. Appreciate your help.
Anything else?
I think that's good. Thank you.
Right, have a nice weekend.
Do the same.
I'll see you next week.
Peace.
Bye-bye.